Hi everyone. Now, after the first example, which illustrated the design of a PID and a model predictive controllers for a linear model of the continuous stirred tank reactor provided by Robert Babuška. In this video, I will try to describe the use of the module. Well, we have already seen the use of the recursively square algorithm with forgetting factor, which, as you remember in the previous movie, was proposed for example, derive an estimation of the disturbance that can be implemented, that can be used by the model predictive control in order to compensate for the model reality mismatch. So let's try to, in this first example, to download 3 files. The first file is called RLS FF, which is a function that implements the recursively square with forgetting factor. And a second file is called example RLS switching model. So we are using the data generated by a switching model. So we are assuming that our data are generated by a model where a parameter is changing, and we will see the effect of the parameter estimator. And then we are considering the Simulink system, which implements the same for the script files implemented in Matlab. So let's see the first example. So let's open the main file, which is a function file. This one. So I'm going to brief comment it. And as you can see here, this function is using the as inputs the output and input data organized in a vector, and the assumed order that is used for the generation of the regressors, and then the lambda. The lambda, of course, is the forgetting factor. And we have this function is generating the estimated parameters in theta hat, the estimated output y hat, and the accuracy. This is the covariance matrix. And if you look into the function, we can recognize after some control functions the generation here of the predicted output, and then depending on the estimated parameters, which are inside a loop, and then the construction or the computation of the estimation error, and then the computation of the covariance matrix P, and then the computation of the gain, which depends on the covariance matrix and the C phi, the actual regressor vector. And then we have the updating law, which updates the current vector of your parameter depending on the gain and the current error. And then we have the update of the matrix. And this is the this is the function. Then if we open the script file, is example RLS model. we can see here that we are assuming a model order of 3 and a forgetting factor which normally should be, let's say, is in between 0.95 and 0.99. And so you can tune here the lambda, the best lambda you think that can be obtained from your data. And then you have here the call of your function with the output, the input, the order, the assumed order for your model, and then the lambda. And then we have some plots, some pictures. Then let's see the generation, which is the generation file, which is obtained in Simulink. Then we open the Simulink file. Let's see this one, parameter change. This file was intended for because we assume that an external signal is actually changing the parameter. Well, the change of the parameter can be due to, for example, a fault or a changing in the working condition of your system. And then we can obtain these. And let's try. Okay, now we have. Let's see if we can open it. Okay, so we have here the generation of the inputs and the output. Well, in this case is single input, single output, and if we run this model, well, you can see the switching model is obtained as a third order model, autoregressive with an exogenous input. As you can see here, we have the exciting input, and then we have the switching parameter, which is changing in the middle of your simulation. Well, the simulation time is 120 seconds. So we have a sample time of 1 second, so we have 120 samples. And if we run our model, okay, we can see here that the input okay, we can see here that in this case okay, you can see here that when the parameter is changing, the variations of your model increases. So it means that the system becomes sluggish, as is said in technical term, and then we can, once we have generated the data, we can see also the variation here of, okay, you can see here that when the parameter is changing, the effect on the output is you have a higher variation of your output. And then after this change, we can launch the main script file, which is this one. So you have now we have the data, and then we can see here that we have a change in the parameter of your in the middle of your simulation, and the predicted value is very close to the measured output. But you can check that if you, for example, increase you decrease the forgetting factor because perhaps you want to obtain a faster response. You can see here that the parameter is tracked in a very fast, in a very quick way, but as you can recognize here, the reliability, so the accuracy of your estimation is deteriorated because it's due to an amplification and an increasing of the noise on the so you are filtering more noise in your system, so it deteriorates the level of your estimation. So this is an important point, and as you can see, if, for example, I'm selecting 50, 0.5, which is really bad value because it's too small, and you can see here that in some cases you can miss the change of your parameter. But in another case, if you increase the number of your forgetting factor, and perhaps you can see here that the tracking is lower, and as a limit, you can see here that if you put 1.0, so you obtain the same at the end, the same result of the classical least square, if you remember. And so this is the example of the use of the recursive least square can be exploited for as an integrated module for your, well, not directly in the design of a controller. Of course, you can use it for example, estimating a parameter, and then you can use it in an example of a design, perhaps of a gain scheduled PID, but it's not the case of the used in this, at least proposed in this course. So we will see a second example of the Simulink module. So you can, as we saw in the previous test case, we can implement the same module, the same recursive. So we have a parameter change for FDI compare, and let's open this other example, and we can now open it here, and this we open. This one. Okay, we can see here that we are actually comparing. So we have the model with the where a change is due to, for example, a fault is modifying the parameters, and we are comparing the real parameters here. Everything is done using the parameter estimator, which is here. So the main problem is that we need to design a regressor vector. Well, as you recognize here, the regressor vector is obtained in this form because the model of the changing parameters is described as a third order. So we have a regressor vector with 3 delays on the output and a delay of 3 on the input, only one delayed input of 3 time steps, and then everything goes into the recursively square estimator. And for this block, you need just to set the number of parameters that in this case is equal to the number, to the dimension of your regressor vector. And of course you need to define your sample time, and here you have the lambda, and you select the output estimation error. So in this case you can export also the signal of here. And if we come back and we launch the simulation, so we have we can see here in the complete version of our model, so now if you remember, I have here the case of the case of when lambda is 1. So we obtain before the middle of the simulation, we obtain the estimation of the classical least square, and then the estimation goes to the overall value determined by the classical least square. And now if we modify the value of lambda here, lambda equal, which now lambda is equal to 1 so there is no adaptation, lambda equal to 0. For example 97, we can see how the simulation changes now. Now it's faster, and now you can see here that after transition, we are able to track the changed parameter with quite good accuracy. But if you, for example, equal to 0. As in the case 0.7, which is a very small value for our adaptation, we can see that the accuracy is worse, because you recognize that we have the increase in the filtering or the effect of the noise. So the accuracy, well, the tracking capability is faster, but the accuracy is worse. So you have a trade-off or a compromise between the accuracy of your estimation and the velocity in the tracking error or the tracking velocity. So it's something that you need to evaluate in advance and to choose the best or the most appropriate forgetting factor. As in order to, before concluding, the best value normally is in the range between 0.95 and 0.99. So it's something in the middle, which is can be chosen as, for example, in 0.97, which provides quite good results. So if you want, we can also put lambda equal to 0.95, which can be quite good. And let's see if we see, and you can see here that the tracking velocity is improved and also the accuracy, but we don't want to deteriorate too much the accuracy of our estimation. Okay, and this module can be if you remember, it was used, this parameter estimation module was used in the previous project, because we were able to show that it can be integrated with, for example, a model predictive control in order to obtain a better control of our nonlinear system. So, okay, thank you for your attention.